Why hello, I didn't see you come in. Welcome to RubyConf 2020. Happy Friday. I know maybe today isn't actually Friday, but the thing is, it's always Friday somewhere, so we have that going for us at least. I'm going to be talking to you about automatic GC compaction in Ruby 3.0. Now, this talk is a 45-minute talk, but I've done my best to compact it down into a 30-minute talk. I really wanted to call this presentation Reduce Memory by Using More, and I will talk about that. I think it's an interesting phenomenon, but really the main topic of this presentation is about automatic compaction in Ruby 3. So that'll be the bulk of this presentation. So my name is Patterson. I'm also known online as tenderlove. This year I started a new job. I work for a small startup company called Shopify. And at Shopify, I'm a full-time Ruby and Rails developer, and I mean that as I'm working on Ruby itself and Rails itself, and that's my full-time job at Shopify. And I feel really lucky to have this position, so I feel really happy about it, and I want to tell you all about the development that I've been doing at my job so far. So that's mainly what I'm going to be talking about today. I'm on the Ruby and Rails core team. I'm also the inventor of the analog terminal bell, which if we have time at the end of this presentation, I will tell you all about this invention of mine. So let's talk about Ruby 2.7. In Ruby 2.7, I introduced a feature called gc.compact. And this feature allows us to save memory by filling in spaces in our heap and eliminating fragmentation. And we can kind of compare it to this old MS-DOS utility here called defrag. But instead of cleaning up your hard drive, this actually cleans up your memory. So rather than rearranging the fragmentation on your physical media, it's actually in memory on the machine. This program here demonstrates the effectiveness of compaction. Essentially what it does is it loads a Rails application, then runs GC to remove any garbage in memory, and then compacts the heap to remove any spaces. So using this, we can actually look at the effectiveness of compaction. So here's a graph of your memory layout before performing compaction. So this is what your memory looks like before we've compacted the heap. The green dots are green and black dots are objects, and white dots are free space. So we can see that this is a fairly fragmented heap. This is the layout of the heap after we've run the compactor. Again, the green and black dots are regular objects, and the red dots, those are objects that couldn't be moved. But you can see in this graph that all these dots are actually much closer together. It's kind of hard to see, but this graph is actually more narrow than the previous one, which means it's actually consuming less memory. So before we dive into my current work, or the work for Ruby 3.0, I want to cover the existing algorithm for compaction because that's going to help us drive the implementation of the new algorithm. So the compaction process has two steps. First, it moves objects around, and then it updates any references. So imagine that we have a heap layout something like this, similar to this. Blue squares represent live Ruby objects, and white squares represent empty slots. Yellow squares represent a forwarding address. The compaction process requires two pointers, one at the beginning of the heap and another one at the end of the heap. And the one at the beginning of the heap is called one is called the free pointer, and the other one is called the scan pointer. So we have one that scans for free slots and one that scans for objects to be moved. So what happens is we start with the two pointers at either end of the heap. One of them scans right, the free pointer scans right until it finds a free slot. Then the scan pointer scans left until it finds a filled slot. And once it meets those conditions, it actually swaps the two and it leaves a forwarding address. So what was in slot 9 is now in slot 3. And we repeat this process with the free pointer moving until it finds a free slot, the scan pointer moving until it finds an object, and then swapping those and leaving behind a forwarding address. We repeat this process until the two pointers meet, and once they have met, we've actually finished moving around all of our objects. So here's exactly the same layout as before, but this is in the state before compaction. So maybe some of the objects have references to each other kind of like this. When the objects get moved around, the references become bad. So let's say it looks like this after we've moved the objects. So now these references are pointing at forwarding addresses. So after the objects have moved around, since the references are bad, we need to update them. To do this, we just simply iterate over each object in the heap and then update it. So in this case, object 1 references object 7, but the object at 7 was now at 4, so we have to update the reference. The next object 2 is pointing at 6, but it needs to 6 move to 5, so we have to update the reference, and we repeat this process for all of the objects in memory. Now, once we've done this, we can clear out any of the forwarding addresses, and compaction is complete. So this is the existing compaction algorithm. So I want to talk about my personal goals for compaction. I want compaction to save memory. So overall, this should save memory in your application. That seems like a pretty important goal. I also want it to be automatic, so you shouldn't need to run GC compaction yourself, or developers shouldn't need to know about it. It should just occur automatically. Another goal is that it should be concurrent, meaning that it can happen at the same time as other processes. So let's say your program can run and then we can do some compaction at the same time. And also it should be fast. So I want to discuss each of these goals one at a time. So first, let's talk about saving memory. Here we can see what the heap looks like before and after compaction. The number of objects are the same, but after compaction, the heap is actually more narrow, meaning that we use less memory. And since objects are packed together more closely, it means that we get better copy on write performance. Now, so I want the compactor to be automatic and the developer to not have to know about it. So it should be able to run and just run automatically, and we don't need to bother or worry about it in our programs. Unfortunately, today you have to call gc.compact in order to run it. And the way that we typically do this, like this is what we do at work, is first we load all of the Rails load our entire application, like in our case a Rails application. Then we call gc.compact before we fork any processes in our web server. Now, unfortunately, we have to call gc.compact ourselves, which means that this is definitely not an automatic process. So next, let's take a look at concurrency. Now, since we have to call gc.compact ourselves, we already know that the compactor is not concurrent. So it doesn't run at the same time as everything else. We have to call gc.compact and it runs on its own. So I want to talk about an implementation problem of the compactor and how this relates to concurrency. So when objects are moved, the destination slot needs to be empty. And this doesn't sound like a problem exactly, but it does mean that GC steps need to occur in a specific order. So we have to have an empty slot here, which means that before we update any objects or before we move any objects around, we have to do a full GC. So we have to clear out any slots so that we can move objects into those cleared slots. So this means that we have to run the sweep phase before we can run the compaction phase. And of course, if we want to run the sweep phase, that means we have to run the mark phase. So we have to do all these steps in a very specific order. So what this means is we're not able to run this concurrently. The GC steps require a very specific order, so we can't really say that this is concurrent. We can't run the compactor at the same time as anything else. It has to be run in a very specific order. So the final goal is speed, and maybe the compactor is fast, but since it can't be executed concurrently with a program, we can't really talk about speed necessarily. Today, we just run gc.compact and it takes however long it takes, and we do that before we serve any requests, so it actually doesn't really matter today what the speed is. But if we want it to be automatic, then we do need it to be fast. Being fast requires that it's also concurrent. So we can't really talk about speed until we have a concurrent compactor. So I can't really judge where this goal is yet. So in order to make the compactor automatic and fast, both of those depend on making the compactor concurrent. So that's the problem I would like to talk about today, is how we can make this process concurrent. Ideally, it would be best if we were running concurrently with other Ruby code. That way we can reduce the amount of time your program pauses. But this is very hard for the first try, and I don't like doing hard things, so I wanted to start with something a bit easier. Instead of making it concurrent with Ruby code, I've decided to make it concurrent with the free step, or the sweeping phase, in the garbage collector. So for the first implementation, we'll change the GC steps a little bit so that moving objects happens concurrently with sweeping. So instead of having a linear process that looks like this, we'll have sweep and move happen at the same time. So let's take a look at the sweep process and then talk about how we can integrate the movement process into it. I'm not going to explain the marking step, but after the marking step, any objects that are going to stay alive will be marked. And we have a mark bit. You can see at the top of this graph there's a mark bit, and any of those objects that are going to stay alive are marked in the mark bit. And any objects that are not marked, those will be collected. Those will be swept. So the sweep process, essentially what it does is it just looks at each object, and if the object is marked, it moves on to the next one. If the object isn't marked, then it will free the object. And we just repeat this process for every object in the heap. Yay, we swept. Okay, so now let's look at how we can combine this sweep phase along with the movement phase. The sweep cursor looks very, very similar to our free cursor, so we should be able to combine these processes. First, we had a scan cursor at one side of the heap, just like we had in the original compaction algorithm. And then the sweep step remains exactly the same, but instead of freeing an object, we know that this slot is empty. At that point, what we can do is we can tell the scan cursor to move and find an object to move into that swept slot, and we just swap the locations and leave a forwarding address. And then we can just repeat this process for the entire heap, and when the two cursors meet, the sweep cursor and the scan cursor, we know that we've moved all of the objects in the heap. Now at this step, we pause the sweep phase and then we go into the reference updating phase. So while the sweep step is paused, we update references exactly like before, where in this case, 1 pointed at 6, but it moved to 5, so we update that reference. And then 2 pointed to 7, but that moved to 4, so we update that reference as well. And we just repeat this process exactly the same way that we did in the first compaction algorithm. Now, after reference updating finishes, we can just continue sweeping the heap as normal. And one nice feature about this is that the sweep step will naturally remove any of the forwarding addresses because those are just locations that don't have any references. So it will automatically free up any of those slots for us. So now compaction is complete. So I implemented this algorithm and it seemed to work fine, and you can go look at the pull request at the URL here. And the GitHub build was working, so I thought everything was good and I decided to merge it. But after I committed the patch, build started failing, so I reverted it. Unfortunately, I had to revert it. Now, what was the bug? What was the problem? The algorithm seemed fine, but the build would fail, and it took me a really long time to figure out why, but the bug went kind of like this. In Ruby, we have classes, of course, and classes are objects, and here is a hierarchy of 3 different classes. So Ruby internally tracks the parent and child of each class like this. So they have kind of a relationship like in this diagram. A child has a reference to a parent, and the parent has references to its children. Now, let's say one of the classes gets garbage collected, or all the references go away. If class C gets deleted when the GC frees class C, C must be removed from A. Then C can be freed itself. This means that during the GC sweep phase, the class C must access class A and say, hey, I need to remove myself from your list of descendants. So let's look at the same process, but from the perspective of the garbage collector. The sweep cursor finds the C class, the C class isn't marked, so we need to free it. The C must be removed from A's list of children, so it reads A's memory and then deletes itself. Then the GC removes the C class itself. So now let's take a look at exactly the same process, but when compaction happens. So this process, the process for sweep and compact is exactly about the same, but when it comes time to sweep the C class, you'll see here that unfortunately the A class has moved. So sweep gets to C. Come on, sweep. Yes, sweep gets to C, and now it needs to remove itself from A, but A has moved, so it's pointing at the wrong location, and now the program will crash. So if we go look at the crash report, or if we go look at the core file, we can actually see here that that's exactly what the problem was. If we look at the object's parent class, that parent class is actually a moved address, not class A like we wanted. So what do we do about this problem? How can we fix this? The way I chose to fix this problem is to introduce read barriers. So what are read barriers? Read barriers are just functions that are called when something is read. Anything is read. So for example, if an object is going to be read, then we can use the read barrier to put that object back into place. So in the case of our classes, if class C tries to read the memory of class A, the read barrier can execute and then move class A back into the location where it used to be, or where C is expecting it to be. Now I'm a really lazy developer, so I wanted to do something easier. I chose to use the mprotect system call. This function allows us to protect a region of memory, and we can mark the memory as having no access. Anytime something tries to read from that memory, an exception occurs, and we can handle the exception. So let's see how this fixes our bug and then talk a bit about mprotect. So this works exactly the same as the previous algorithm, but after we move an object, we protect the page. So each time we move an object, we remove page protection, and then after the object is moved, we add protection to that page. Yay, protection. So you can see here in this graph, every time we move an object, we add protection, but before we move the object, we remove protection. Now, at this point, when C tries to read address 9, an exception will occur because the memory is protected. Then the exception handler can remove protection and move all of the objects back to their original location. And what this means is that the sweep step can continue just as usual. Now, there are some problems with the system call, and we're going to talk about those problems. First off is that whenever we mprotect a region of memory, that region needs to be aligned on a multiple of 4 kilobytes. And the size of that region also needs to be a multiple of 4 kilobytes. So the address of the memory must be a multiple of 4 kilobytes, and the size is a multiple of 4 kilobytes. So we need to protect pages of memory where Ruby objects are allocated. So keeping in mind the requirements of mprotect, let's look at how Ruby allocates heap pages. So this is the code in Ruby where a page of objects is allocated. We can see here that it's aligned on heap page align. And if we look at the value of heap page align, that's essentially 1 that's shifted to the left 14. And that value is 1638. It's 16 kilobytes, which is evenly divisible by 4 kilobytes. So this first requirement is met. The addresses are a multiple of 4 kilobytes, so we've met the first requirement. Now the second requirement is the size. The page size is this heap page align. It's a really some complicated code here. Heap page align minus some stuff with some other stuff thrown in here. And if we do all the calculations for this, we'll see that the size is 16344, and it turns out that that number is not a multiple of 4 kilobytes. So we have a problem here. The page size is this number that can't be protected by mprotect. So we can't use mprotect in this case. Now, this got me thinking, why not allocate exactly 16 kilobytes? if we allocated exactly 16 kilobytes in width, we could use mprotect as a read barrier. So our early calculations subtracted a variable called required size by malloc, and what's interesting is that this value is exactly 40. And this is really, really convenient to us because 40 is exactly the same size as a Ruby object. Meaning that if we expanded our heap pages to be exactly 16 kilobytes, it means that every page could actually store one more object. So I did exactly that. I sent a patch to Ruby to expand the heap by one more object so that the pages were exactly 16 kilobytes. So in order to test the patch, I ran RDoc as a benchmark and essentially just recorded the heap size as we were generating RDoc. This is a graph of the memory usage over time. The x-axis is time, the y-axis is memory usage. The red line is the master branch, and the blue line is the branch with my patch applied. Now, I ran the benchmark 50 times, and from the graph we can see that with the patch applied, RDoc generation usually uses less memory. So what these graphs are saying is that if we request less memory, we actually end up using more. Or to say that, flip that statement, if we request more memory, we actually end up using less. Now, why is this? The reason is because jemalloc uses fixed size blocks, and 16 kilobytes is one of those blocks. So if we allocate 16 kilobytes, if we allocate something near 16 kilobytes, the entire block will get reserved, but in our case, that ending 40 bytes is just never used. It's wasted. So if we turn around and allocate exactly 16 kilobytes, then that entire block ends up being used. And this is how, like, if we allocate a convenient size for the malloc implementation, it means that we can actually use memory more efficiently and overall reduce the amount of memory that we use. So allocating a good size reduces our overall memory usage. And this is why I wanted to call the talk Reducing Memory by Using More, because we're reducing memory by using more, but again, this is about GC compaction. So this is the entire patch for it. The important part is here where heap page size is now exactly the same as heap page align. So we made those two values exactly the same. Now pages are aligned at 4 kilobytes and the size is a multiple of 4 kilobytes. So we can actually use mprotect. And I made a pull request for it. Here's the URL for it. It combines compact and free. Now, unfortunately, it's way too slow. If we just compare gc.compact between the master branch and the feature branch, we'll see that the version with the read barrier is about 4.5 times slower than the original version of GC compact. Even though compaction is concurrent, making it 4.5 times slower is just too much. So what is the problem? What is too slow? Of course, in order to find what's too slow, we have to profile the code. And typically when I'm profiling Ruby code, I like to use this tool called StackProf, but this is for profiling Ruby code and we need to profile C code. And in my case, I'm using macOS, so I like to use instruments. And I'm going to give you an example of how to use instruments with this, with Ruby. So this is the command I used, and I've broken it down into several lines so that it's easy to explain. First, we just have the instruments command. Then we have to tell it what type of profiler we're using. In this case, we're doing a time-based profile. Then we give it the binary that we're going to target, which is Ruby in this case, and then we can give it any arguments, which here I'm going to be requiring Rails and then running gc.compact. Finally, we can use the open command to just open this profile, and it'll open it in the instruments GUI tool. So if we open it in the GUI tool, we can see where the bottleneck is, and the bottleneck is right here calling mprotect. So we can see that our bottleneck is the mprotect system call itself. I usually have two strategies I use for improving performance. And the first strategy is just to make the function faster. Like whatever it is, we'll make it faster. Now my second strategy is if I can't make the function faster, I try to just not call it as much. Now in this case, I don't think I can speed up mprotect. That might be a little bit above my pay grade. But also, like, who knows what versions of mprotect people are using in the wild. So in this case, and also I don't want to tell people, hey, upgrade to Aaron's mprotect. It's much better, I promise. So I don't think I'm going to be able to speed up mprotect. So what I would like to do is I would like to call it fewer times. So I'm going to use the second strategy, which is don't call it so much. So let's study the current algorithm. Before we move an object, we have to unprotect a page. Then after we move an object, we have to reprotect the page. So both protection and unprotection call the mprotect function. So when we lock a page or unlock the page, we have to use the mprotect system call. Now this means that every time we move an object, we're locking and unlocking. So for every object we move, we have to call the mprotect system call twice. And that is a bit too much. The number of mprotect system calls is 2 times the number of moved objects. So the way I chose to speed this up is to batch up object movement. So we only need to lock or unlock a page when we're moving objects. So what I thought is that maybe if we move many objects at once, then we don't need as many calls to mprotect. And a natural place to do the object movement happens to be at page boundaries. So after a page gets swept, we fill in that page. So I modified the algorithm such that once a page is swept, we'll fill that current page. So let's take a look at the algorithm. To batch up movements, first we sweep a page without moving any objects. Now, once the sweeping pointer gets to the end of the page, then we'll pause the sweep process. And unfortunately, this means we have to introduce a free pointer, which will scan the page for any free slots. And as soon as we find a free slot, we can move objects to that location. So we'll unprotect the page, use the free pointer to find any free locations, and then move objects. And when the free pointer meets the sweeping pointer, we know that we're done sweeping, or we know that we're done packing that particular page. Now, I want to point out the performance improvement of doing this. The worst case is that there is only one movable object on a particular page, which means we'll have to call mprotect twice for one object. The best case is that we'll be able to move 408 or an entire page, which is around 408 objects. We can move all of those and only call mprotect twice. So our average case is about 2 mprotect calls per 200 objects, which is actually really great. This is a 200% performance improvement over the previous implementation. So if we compare compaction time, we can see that compacting on master is about the same as compacting on the feature branch with this new algorithm, but we get the added benefit of introducing a read barrier. So it's the same speed, but we got a read barrier out of it. Now, in order to speed this up, we basically had to revert the algorithm to the very first algorithm that I had written for Ruby 2.7. So, however, instead of packing the entire heap, we're just packing one page at a time. So the algorithm went all the way to something more complicated, then back to the original, unfortunately. But now that we have a read barrier in place and per page packing, it means that we can run the compactor automatically on all major garbage collections. So I'll show the patch here, but it's very, very anticlimactic. This is the entire patch. It's a little bit upside down, but all we do is when we enter the mark phase, we check, is this a major GC? If it is, then we'll enter compaction mode. And then when we enter the sweep phase, we just kick off the compactor. So we can actually see the compactor in action. This is an example. When we run gc.start, that implies a full compaction as well. So we can see that the compact count increases when we check the GC stats. And in the next section, it just allocates a whole bunch of objects until a major GC is kicked off. And we can see that once a major GC is kicked off, and indeed that executes a compaction as well. So let's take a look at what's in Ruby 3.0 with regard to compaction anyway. Here's an overview of the API that's going to be in Ruby 3. We can enable automatic compaction and we can disable automatic compaction. We can also check statistics about the last time that we did compaction. And of course, we can still manually compact the heap. Now, auto compaction is disabled by default, and I want to talk a little bit about why before we end the presentation today. I want to return to the topic of speed for a second. So I said that I want it to be fast, and we need to figure out exactly what fast means. And the only thing we really have to compare to today is major GCs. So we have a major GC, and we have to add automatic compaction to that. So what kind of overhead does automatic compaction incur? It can't be free, but what is the overhead exactly? So we want to enable compaction, but at what cost? So to measure the cost, I generated RDoc for Ruby itself and then measured the time that it took for major GCs while RDoc was being generated. Then I ran the same test but had auto compaction enabled. That way we could see what the overhead was, or what the cost was of enabling automatic compaction. So this graph shows 10 different runs of RDoc being generated. Blue lines are the with automatic compaction enabled, and the red lines are without automatic compaction. The x-axis is the GC count, or the GC count, so 20 indicates the 20th major GC, and the y-axis is the amount of time that GC took. So we can see here that the blue line is with compaction, red line is without compaction. So the difference between those two lines is the overhead that compaction incurs. And we can see that it really does slow down major GCs. So this is another graph that shows the throughput of the garbage collector, or how many objects per second can we do on each GC. On the left is with auto compaction enabled, and on the right is without auto compaction enabled. Again, we can see like having compaction enabled reduces our throughput. So lower is worse, higher is better. So we can see that indeed, like, the number of objects we can process per second is slower with compaction enabled. So of course the question is, like, should I use this? Which I think is a very valid question. And since I wrote this feature, of course the answer is yes, you should absolutely use this feature. Please use it. But seriously, you probably shouldn't enable this in production because it will slow down your major GCs. If you know that you're not doing too many major GCs, maybe it's fine, but I would recommend not to turn this on in production. However, please try it in your CI environments. Eventually, I would like to make this enabled by default, but we need to find any bugs first. So I think that if we can enable this in our CI environments and then report any bugs, like, I would really appreciate that. So please don't use it in production, but please use it in your CI. So to wrap up, it took me a lot of time to get this readberry into place, especially with this new algorithm that I wrote. And actually, the first time that I tried out this algorithm, it was actually 27 times slower than the original, and that was actually really depressing to me. But it turned out that I hadn't enabled optimizations on the compiler, so I had compiled it with 0 instead of 03, and that's why it was so slow. So then I felt really excited. I'm like, oh, I'll enable optimizations, and I'm sure it'll be fine. But then once I enabled optimizations, it was only 4.5 times slower. So actually, even this number was pretty depressing to me, but because I thought for sure it should be about the same speed. Now, it wasn't until I looked at the bigger picture that I felt good about this work that I had done. This project wasn't necessarily about speed, but it was about proving that we could implement a read barrier in the garbage collector and actually have that read barrier work. And I was able to accomplish that goal. So really the only thing that's left is speed. And the thing is, like, this is a lesson that I relearn over and over again, which is we need to make our code work first. Then once we make it work, then we make it fast. So I keep relearning this lesson, is to just make my code work and then make my code fast. So thank you very much. I hope that I will actually get to see you all in person next year. Thank you. Woo! We did it. I'm going to end the recording here.